Good afternoon, ladies and gentlemen, or good morning or good evening, wherever you are. Thank you so much for joining us for this panel discussion. Panel discussions are always a highlight of ALTA conferences, and we're very happy to offer this panel discussion online so that people can join us from all over the world. I'm now going to hand over to our panel chair, Alan Taylor, who's going to moderate the discussion. Over to you, Alan.
Okay, thank you, Alison, and welcome to the panel. I'm sure that you've all been enjoying some excellent presentations on various aspects of membranes. I think we've had some great papers, and I really appreciate the way this has come together, because in the uranium industry in particularly, membranes is really making an impact, and it's going to have a bright future. One thing we didn't mention is in rare earths, because that's the other part of this day, and as we go on through the hour, maybe someone would like to contribute on how how it might be incorporated in rare earths, but we'll leave that for the moment. I thought we'd just start off with asking our keynote speaker this morning. I thought that, and of course his presentation later on how things went at Carlicera and Langer, and I thought I'd just ask him to talk about major lessons learned from the membrane applications at Carlicera and Langer, and the Langer plants, and perhaps some comments about would he do anything different if he had to start again? And that by starting to talk about that, we maybe flush out some topics that we might want to discuss. So Daryl, if you wouldn't mind starting out by addressing those 2 points.
Daryl, there's no sound. You might want to unmute your mic.
Yeah, okay.
So start again. Thank you for that.
The space bar is meant to unmute, and it suddenly isn't. So in terms of lessons, both installations went very well. Obviously, lessons were learned in introducing this technology. And I guess the outcomes in themselves are somewhat of a lesson. Both installations, as I said, and I said in the paper, were very, very successful. And a good part of that is down to 2 things. Number one, we were given quite free hand, not a lot of money, but we were given quite free hand in terms of engineering. And you know, Mark was involved in that, and many times we just went back and said, not having that, do it another way, and indeed we did. The other area there, I think, is the design. The design was really very detailed. We were very careful to know what we knew and know what we didn't know, and seek prior mitigations or potential mitigations of those areas where we had real risk. All of which sounds like just prudent design, and I think it is prudent design, although I've got to say I don't think it happens all that frequently in the modern world, or in contemporary practice. Or to put it a better way, perhaps too frequently in contemporary practice, design is just a necessary evil one has to have, and you get over it as fast as you can so that you can get and build the plan. That can have dire consequences, and in bringing on a new process, a new technology, it can have catastrophic consequences. So we were very careful in that regard, and it bore fruit. So, if you like, not a negative lesson, but a positive lesson. I think too, in Carlicera, you know, when I first heard that design membrane life would be 11 days, I was somewhat shocked. And I immediately thought, good heavens, this simply cannot be economic. You know, we may as well stop now. This just won't work. But indeed it did. Even with a design life of 11 days, the Carla-Cara installation, in terms of the documentation used to justify it, was a lay down misere. It was extraordinarily positive.
So why was it so low, Darryl? Why was it 10, 11 days?
The life, I've actually answered your query, but I'm happy to answer again, Steve. It was the strength of the acid solution. By the time we got to the end of the Christmas tree, the retentate was approaching 4 molar sulfuric. It was pretty powerful. And Mark, correct me if I'm wrong, but I'm pretty confident that the membranes we were using were a cellulosic base. So.
No, they were polyamide.
Polyamide. Okay. Even so, not really resistant to that strength acid. It was, however, and in the fullness of time, we got about 2.5 times that life. We got 25 to 30 days. We're on easy street.
And look, just to add further to what you said there, Darryl, we actually did trial acid-proof membranes as well as acid-resistant. And as we saw earlier in Leslie's presentation, the rejection characteristics and the flux rates of acid-proof membranes have a very different behaviour than what we're terming acid-resistant membranes do. The downside is the membrane life, but the upside is their improved performance. And on an economic evaluation, the acid-resistant membranes proved to be a more economical choice, even with a 11-day change-out, which once it averaged between 30 to 50 days, depending on the back end or the front end of the membrane plant, it turned out to be the correct choice. We did have, as Darryl said earlier, always had alternative plans, and the plant was designed that we could have gone to acid-proof membranes, and that would have required a second pass to achieve the uranium rejection and the acid recovery that we were targeting. Would have effectively doubled the capex, or not quite doubled, but increased the capex cost, because you're now going to a second pass. So hence the initial choice was to try and lower capex, and we're prepared to take a bit of a hit on the OPEX, but the membrane life, in reality, we didn't actually take that hit in the end.
Well, the membrane manufacturers are notorious for limiting the mode of operation so that they have a really tight warranty, so they never have to pay out anything.
Absolutely.
The reality is, in the real world, where we're treating or thousands of our oil plants in all sorts of different industries, is membranes are much more resistant than the manufacturers will ever claim that they are.
Yes. And in our case, we're so far outside anything the manufacturer is willing to publish, then warranty is just a far off dream.
Yeah, exactly. But what happens is people say, oh, we can't run a membrane plant on this water application because it's out of spec. Well, ignore that. Just do it anyway because the benefits are so great.
Exactly.
And that's what people are starting to realise. To heck with the warranty. It doesn't matter. If we can go from 3 months life to 4 months life, that's 25% improvement. That works. Even more so in mining than any other industry.
That's right, Stephen. Philosophically, if you're really relying on a warranty as your backup plan, you've got a serious problem.
Mark, it's unusual to be so confident about how things last and so on, because it's such a great advantage. Doesn't happen very often. But from the engineering point of view, what lessons have you learned about it, and what would you do things differently in the future?
One of the things is you could really almost divide your issues up into technical issues, which is plant design, feed chemistry, etc., and then site or / operator issues. I'd like to think that the technical issues, we sort of covered all bases. And so we had a plan B, if you want, if we had ability to put in extra membrane housings, additional feed pump pressures available to compensate for increased osmotic pressures, etc. But some of the issues that were the first time we lost membranes at Langer Heinrich was when we had a water change. The feed water that they're using on the plant, we had a significant increase in sulfates, and we had a loss of membranes on the tail end. Not much you can do about when operators have issues with something that they do that changes your process feed conditions, and now that pushed the membranes into a supersaturated area. So that's one of the lessons learned, is how do you, things we weren't testing for on a daily basis. We could have, otherwise we'd somehow tested for a change in feed in some of these trace components that didn't normally undergo laboratory testing on a daily basis. Potentially you could have picked up these sorts of issues. Other one is operator competence. We did a very comprehensive training of the operators when we started the plant. But in the fullness of time, where the plant ran 2 to 3 years, as you can imagine, the turnover of operators, it can have a direct impact, especially when the plant actually ran so well. It was a fully automated plant. You pressed a button, it did all the full startup. That was a great way to run a plant. But when you had any sort of issues, operators had no idea what to do. And when you're talking about an African environment, with the level of competency for troubleshooting or recognising, is it a real issue in the plant? Is it a sensor issue, or have you got a mechanical issue? They were some of the real-time or real-life issues that cropped up on the plant. Yeah.
Good. Anyone else want to chip in on lessons learned from that? From the cleaning point of view, I think that that we've had some good input from Stephen on that, and obviously that's a major input. How about a new operation, Leslie? From your point of view, you're looking ahead. You're going to run a pilot plant. Do you see challenges in that you're going to have to look at from the pilot plant, or do you think things are based on what's been done and on these other 2 plants? It's going to go pretty well for you?
Well, Alan, for us, because it's a class 1 pilot, so it's installed as a pilot plant and goes directly over into operation, purely from, I would say, an implementation point of view, because Kazakhstan has very specific rules with regards to new systems, new technology integrated into the uranium processing circuit. So there was a lot of reasons why it was classified as a pilot plant, but it processes the full flow rate for us. So the benefits being that we're on a satellite processing facility, so the concentrate produced from the membrane system itself is still blended in at the central processing facility. And what we expect to see is that not only will we have the benefits on the satellite processing facility, but that we should see the holistic impact on the plant-wide reagent savings, transport costs, not just on our side, but also at the central processing facility itself. So we have all of the previous experience from the Trekopi plant that was done in 2011. And we have a similar system operating in Canada, which has collected all of the data that we've needed to use as input into the plant itself. Once again, I think what becomes quite apparent from all these systems is that the processing itself is the straightforward approach, and that's a training thing to get it handed over to the client, where the cleaning for every system is unique. You will spend your entire life optimizing the CIP cycles for these systems to make sure that you can get the best life, good performance, and some longevity out of the system itself.
Have you found a growing interest in Kazakhstan? Obviously, there's a lot of ISR plants out there in using membranes. Is there a growing interest there?
Yes, actually. So we have a pilot plant that is traveling around from site to site, doing all of the data collection and then design, and then it moves over to the new site with Kazatomprom in particular. They were all, obviously, everyone wants to be first to be second. So they were waiting for the result to come out of Kazakhstan, and then use that to implement onto the other sites, use it sort of as the baseline for the processing. Also, because there is a lot of satellite processing in Kazakhstan, it has a major benefit for transport costs because the distances get quite far. We were only 40 kilometers away, but some of the sites are finding eluate concentrated solutions, loaded resin for hundreds of kilometers to process.
What about for concentrating feed coming out of the production wells? Has there been any interest in that?
So there are a few projects where we focus on the PLS, typically because the PLS is relatively low concentrations. You can achieve a much higher concentration factor going straight into ion exchange. And there are so many resins out there that have excellent selectivity towards uranium over other elements that if you need to go from 10, 5, what is now 15 ppm averages coming from the ISR well fields to achieve a 30, 40, 50 times concentration factor with ion exchange is much more cost effective than membranes. So the focus typically becomes on the eluate after you've stripped IX, where your acid concentrations are high and your stream flow rates are relatively low, that you can make a big impact on the process prior to precipitation.
Anyone else want to comment on, the focus seems to be on eluates and clean, and that, but what about the broader application? Chris, maybe some comments on, Adrian, how about commenting on REE? I mean, you're involved in that quite a bit. Do you see any applications there?
Just to pick up from what Leslie was saying, yeah, I mean, that's what we've found is that if IX is an option, then that's going to be a cheaper way forward for concentrating up, uranium and that sort of thing. That like one of the applications we've put forward, we see a possibility for it in the carbonate systems because it's a lot cheaper in that case to manage scaling and things like that. But in terms of the REE circuits, it's not an easy one. In your main hydromet processing routes from your rare earth concentrates through to your rare earth carbonates and those types of processing circuits, they're relatively dirty liquors, compared to the back end of an IX or an SX circuit where you've got a fairly clean mix of, uranium and reagents and things like that. Back over at the end of the process in terms of the rare earth SX area where you've got like hydrochloric acid, nitric acid maybe being used to strip rare earths out. Generally, the rare earth concentrations are high. So it's hard there to manage the osmotic pressure as well, even though there are some free acidities that are then need to be neutralized. So it's not an easy one I think if you had a really dilute rare earth solution that you wanted to recover, they would come into consideration. But again, it would be weighed against other technologies. So it's not an easy one at the moment.
It also depends on the stream you may be looking at as a direct feed on a rare earths on the main process. I agree with you there, Adrian. But most of these rare earth processes have a lot of side streams, and we've been close to 12 months now working with an Australian rare earth company and we're treating with membranes some of the side stream processes, and that's where you have to look for the application. Membranes certainly aren't a snake oil that fixes everything. They've got, as Daryl said in his presentation, they've got some unique properties, and you have to be able to see in the process flow sheet where it actually fits in. And so I agree with you, Adrian, that on the main process flows, the osmotic pressures, the concentrations, it's an unlikely process. But on a lot of the side streams, on some of the and cleaning up some of the other side streams, there's some very interesting applications that are currently under testing. Due to commercial sensitivities, I can't say too much more, but it is certainly happening, and hopefully this time next year we'll be able to talk about it in much more detail.
Okay, I've already booked you down for next year to talk about rare earths.
Actually, we have two membrane systems operating on PLS rare earth concentration. So the one is treating about 200 an hour, and the other one is treating 140 cubes an hour. So on the rare earths, the PLS side has a longer payback period. So for us, compared to uranium, it's a different ballgame because we're used to like under a year payback periods for these systems. With rare earths, you're looking at like 2 to 3 years. The PLS is split into a high concentration and an intermediate concentration. So we have a system operating on both of those streams to concentrate a mixed PLS. The acid coming in is about 30 to 50 grams per liter. So the focus is much more on the concentration of the rare earths to upgrade them to a concentration where when you take them to ion exchange or scavenging or anything like that, that you have a much lower volume to treat going into the back end of the process. And then the other application, it's volume reduction, and also to take out a lot of the chlorides that's coming in with the feed source. So there we're looking at monovalent passage There's also it's a phosphoric acid a feedstock coming in, so phosphate-based monazite. And because of the phosphate, you create a lot of phosphoric acid, which is monovalent and neutral up front that you can pass straight through the membrane. So there, the concentration factors you can achieve is 2 to 3 times just straight in your PLS.
I think too, Alan, on the uranium side, particularly in carbonate chemistry, treating PLS with membranes has really significant potential.
Yeah, as I say, Deep Yellow's submission, as you'd know, Daryl, they're using membranes on their PLS solution as a concentrating step.
Who's that?
Deep Yellow, they put forward in their application to the Namibian government for their environmental impact statement, their process flow sheet has membranes on their PLS.
And what sort of leaching do they have? Is that heap leaching?
They'll be able to speak better to that, but yeah, I don't believe it's heap leaching.
Okay.
No, we wouldn't go near heap. So it's concept studies out in public. So the concept study spoke of using autoclave leach, and one of the advantages is that these are carnotite bodies. So the kinetics really respond to even mildly elevated temperatures, and we don't need to go very far past atmospheric to get stunning changes in kinetics. So the leach will be high temperature. We're not talking HPAL. We're talking pretty low temperature in the autoclave range. Pretty low temperature and very low pressure.
Okay.
But yeah, we're looking to process all of that PLS with membranes, and we saw some pretty dramatic reductions in operating cost with what we did at Langer. We expect to see a similar scale in the reductions we get here.
Yeah, well, that's pretty.
We're seeing a lot of projects whereby, in all aspects, where you're starting to get some fractionation. So by using NF and then RO, so you can either split off your divalent ions, reduce the risk of calcium sulfate scaling with nanofiltration, but also split off your precious metal monovalent and divalent ions, and even having NF and RO elements in the same pressure vessel. There's all sorts of different techniques of fractionation of those water streams going on. I mean, in all the lithium recovery in northern Argentina, there's extensive use of NF and then splitting off to RO. We're looking at geothermal lithium extraction processes now, all incorporating membranes. And the membranes are just a pre-concentrating step to then ion exchange. You can increase the efficiency of the ion exchange and selective ion removal with resins, but it improves that process if you can concentrate up 2, 3, 4, 5, even 10 times with membranes. If you split off the scaling species, it's that calcium sulfate scale that seems to be the limiting factor.
It's even better, Stephen, if you can get rid of the ion exchange altogether.
I couldn't possibly say that.
Yeah, well, in uranium, in alkali uranium processing, it's resin that drives the operating cost.
Yeah.
What about heap leaching? There's a dilute solution, and
now, Alan, you've been talking about. Are we talking about uranium now? You've been talking heap leaching for as long as I've known you, and I don't think heap leaching is any more de-risked now than it was 30 years ago. Yeah. So, my personal view is if you have to go heap, particularly in uranium, but in many other metals, if you have to go heap, it's because you can't make the project work.
Well, it may be the only ore body you've got. People spend a long time trying to find ore bodies, and if they find one that's heap leachable, they're not going to say, I won't have this, I'm going to try and find one.
No, it's true, and there are heap leach successes. There are, but I would have thought there's probably more failures.
Well, you don't want one, but it's the only one you've got. There's a lot of people who seem to have them. So, but what about, is there anything, just from the technical point of view, is there any reason why you can't take heap leaching thing? And for example, sometimes in a tropical area, you get a lot of dilution, and you can't make production in the plant because your plant is volume restricted, and you want to do some concentration. Is there any technical reason why you can't use it on heap leaching?
No, we've actually done trials on PLS for heap leach, and it's certainly a viable route. But it also introduces other advantages with a heap leach, because you're now doing a membrane concentration step. You can certainly now have higher rates of leachates, and so you can have faster turnaround times. So it's not just the concentration using membranes on the heap leach PLS. You can actually change the kinetics of the heap leach itself, or the not so much the kinetics you're changing, but the application of your flows.
Yeah.
Certainly, we got involved with the large RO plant at Yanacocha in Peru, where basically rainwater was diluting their pregnant liquor, and the membrane is to remove excess rainwater. You're concentrating up that pregnant liquor before it carries on into the extraction process. And that has been copied many places. I mean, there's a lot of dry areas, but you get torrential rain occasionally when you're 3,000 meters up. And that concentrating of the pregnant liquor is vital for those operations.
Anyone else want to comment on it? I think what Darryl said of it being a tool now, that we've got to say, how are we going to use this tool? And I think the industry is just waking up to this. I think RO's been around for a while, but seeing NF now actually incorporated in plants, I think this is a new thought for a lot of people.
Yeah, I agree, Alan. And like any new technology, the next decade is going to be very interesting.
Yeah.
And I suspect we'll see membranes applied in areas where we just haven't really thought of.
Yeah, I remember Darryl, when you and Mark presented a paper a few years ago,
yeah.
and I noticed you said you see it as a game changer in the uranium process. Do you still think that?
Yeah, absolutely. And the game that's been changed, I think, is that the go-to technology for uranium, all of my professional life, has been the acid route. Where I don't think that that's now the foregone conclusion that it once truly was. Membranes offer and they offer more promise on the alkali side than they do on the acid side, in my view. And the alkali processing of uranium has some distinct advantages. It also has some disadvantages, and membranes help to overcome many of those disadvantages in big swathes. Now, at Langer, we reduced the processing operating cost by 50%. In a single introduction of a single technology, that's stunning. I believe in what we can see ahead of what we're doing, we will reduce that by a further 50%. So we'll be down to 25% of where we were before, and alkaline then becomes really competitive with acid. And if you look at things, no, I won't go into quite a specific detail because I probably shouldn't, but there are operations that have examined both alkali and acid processing, and both, and this is not just Carnotite bodies now, this is almost any uranium mineral species. And alkali generally works sometimes better than alkali. Maybe. Sorry, say that again?
A lot slower alkaline leaching.
Yeah, and you can bounce the kinetics. You can bounce the kinetics with temperature. That's easy, and we're much better at doing that now with all the HPAL experience we had. We have, as I said, you don't have to go to those levels. You don't have to go to particularly HPAL pressures because there's generally not too much overpressure.
Yeah.
But I think it'll really change the dynamic. in terms of uranium processing.
Yeah. When I first came into the uranium business many moons ago, there were a lot of autoclave operations.
Yes.
On alkaline leaching. It was very common. And
Yes.
one of the big advantages is the material construction is just not so much small. You generally had to worry about where the slurry level was, and that, but basically get away with ordinary carbon.
Yep.
And so it makes the capital cost a lot lower. But why, just on that vein, maybe for people listening, why would you think that it's better to go alkaline than acid?
Primarily because on the alkali side, most of the penalty metals in uranium aren't there. Vanadium's an issue, and in carnotite bodies, vanadium's there, and there are certainly some elements that cause a problem.
Yeah.
But far fewer than you get in acid circuit. And it's public that Langer went alkali leach circuit, but then swapped over to acid in the refining section of the process. So then you use one chemistry to get rid of most of the problem species, contaminant species. Then you switch chemistry and get rid of the rest. End it with a very pure product.
It's an interesting concept to go up in temperature even, and people think of HPAL, they think of nickel, and you think of titanium lining and all that sort of stuff.
Yes.
But with alkaline, you can think of carbon steel.
You can, and we're not talking the 250 degrees with 50 bars of overpressure.
No, just a little bit over the 100.
Yeah, that's
120, that sort of thing. Yeah.
That's exactly right.
And a lot of plants built that way in the 60s and 70s.
Yes, there were. Yes.
And in fact, Uleri was going to go that way, and he originally piloted that with their Western Mining piloted with pressure.
Yes.
And I switched now to I think to atmospheric, but yeah. But interesting thought.
Yeah, and I think, from the membranes point of view, definitely agree with Daryl there, because you don't have that acid attack problem on the membranes. You can get by on a more standard membrane. As was pointed out, the acid resistant ones have had trouble performing as well generally. So you got a more favorable environment for the membranes, definitely.
Yeah. And you don't have, I think we'll see circuits in the future that don't have SX or IX. And every step you take out is a reduction in operating cost of it, as a general rule of thumb. That's not an absolute.
Yeah. I think I asked Adrian a question on he talked about SX. Do we see it possible to run membranes after SX? What about the organic? As a fact, do we really talk about always ion exchange? Is SX an issue with the organic getting through?
It's definitely a consideration, like we did work on that many years ago in terms of an SX nano process. And, we never got to the point in that case of piloting it, but entrainment of solvent. But you'd think that would be manageable, certainly upping the process risk a bit. And then it's a question of, there's solvent stable membranes, but then you face the same sort of problem when you head in that direction of how good is that flux and rejection performance for one of those kind of membranes. So you want to kind of put in a nice pre-treatment step as opposed to really reject that entrained solvent, and that would be the main, you'd think that'd be the way to go.
Yeah.
And then pilot it. I mean, that's one of the other lessons learned. That's, you look at the applications in Kazakhstan and Paladin's ones, the big benefit they've got compared to a lot of the projects is being a brownfield. I know that presents challenges, but it presents a massive opportunity in the sense that there's an existing operating plant producing liquor. With membranes, you're really faced with one of the challenges. You've got to pilot it for long enough to know what the flux decline will be, so that you've got a robust design basis, And so for a lot of the developing projects that are doing some piloting and lab work and all that sort of thing, how do they produce that quantity of liquor to do that extensive piloting? Yes, you can do small scale continuous demonstration, but there's a big advantage for an existing plant to do that.
Yeah. The question maybe asked everyone, chip in on people watching or listening. Listening might say, well, I've got a project, but what level of test work do I need? Can I do? How realistic is lab work? How, you know, pilot work? I mean, some tools that we have need large scale work to be able to design the things, to worry about, does it plug, does it scale? Can we resolve those things in the lab and on the pilot, or what is the risk there? That whole topic about scale up.
I suppose one of the major factors is how far you're moving away from a known process. In a completely greenfields area where there's nothing similar, the list of unknowns is quite large. Kayla Care is a classic, hadn't been done before. So we had a lot of contingency. By the time we got to Langer, we'd learned a lot from a technical perspective in terms of the mechanical aspects of the plant, and we could was then perhaps more concerned around the chemistry issues. So I suppose the real take out of that one is the further you drift from a known process, the more unknowns, the harder it's going to be.
Anyone else?
Well, that's almost a truism, Mark. However, in both those cases, we really applied, this is a hydromet process. At the end of the day, this is a hydromet process. We're not talking about a physical process where, in my opinion, you perhaps got a greater need for piloting in the conventional sense. So, we completed those designs by locking lock cycle bench work with a decent model, a decent multi-element model, and if the two didn't converge, we kept working. In truth, we did leave some risk areas open, but we made sure we had no mitigations for those risks in going forward.
But you did have actual liquors to work on. You didn't have artificial.
In a sense, we did, but we didn't really, because we didn't have the liquors that were consequential to membranes being installed. So yes, we did. We had guidance, absolutely, but we didn't necessarily have where the plant was going to end up.
A good example there was Langer Heinrich. The liquors we had to test was 60 gram per litre. The liquors we ended up with were 30 gram per litre. When you're halving your liquor concentration, that's a significant change in membrane performance possibilities.
What about membrane plug scaling and things like that? Can that be realistically done without on a new?
Yeah, it's very, very easy to take a feed water analysis and project what scaling issues you're going to have within the membranes. It's very simple piece of software. You're calculating the solubility product of different ions, different scales, and then you can apply different anti-scalants to push that solubility way beyond normal. So calcium sulfate is soluble to about 2,600 ppm. With the right anti-scalant, you can go 10 times past that solubility level. So up over, you can hold 20,000 ppm of calcium sulfate in solution. That way you can extend the window of operation of the RO membrane plant significantly. And you can predict all this well in advance, as long as you've got a decent water analysis, where you can do lots of different variations, change the water quality and see what impact that has. So you create this window of operation that's safe, which gives you the advantages that you want in terms of concentrating up your pregnant liquor or the amount of precious metal you're trying to concentrate, and then see if that's viable for the rest of the process. And that's what we've been developing, particularly now developing anti-scalants that'll work at acidic in acidic conditions, which has always been very, very difficult. Everybody would neutralize feed water to the membrane plant and then operate it, where actually you can operate under acidic conditions and still stop calcium sulfate scale, because that is the main limiting factor for the membrane plant use.
And one of the other things to be careful of with anti-scalants is also then a potential poisoning effect on the downstream operations. Any chemical that's added within the process can potentially have an impact. So while testing on the membranes and getting a positive result on a membrane anti-scalant, you still have to look at that anti-scalant that's now going down to the next stream process. Does that become a poison for precipitation or some other sort of issue? So anti-scalants...
extraction is exactly like that. Yeah.
And that's like everything. There's no one size fits all solution. Some places you have to live with the problem and be restricted to operating pressures and recoveries. Other places, anti-scalants have got a huge role to play.
Yeah, well, for example, if you have stuff you're adding flocculant, you need to test it on an SX before you commit to that. So
Absolutely.
if you add an anti-scalant, you need to test it on the rest of the plant. Yeah.
And I think too, being conservative, you've got to be conservative in your available mitigation tools. So clean in place is an absolute necessity, but we were very conservative about the clean in place schedule we'd require, and we geared up for a lot more CIP at Langer. At Carlacera, we geared up for a lot more membrane changes than we ultimately needed. But there's always risk in any design, whether the design is known, established or not.
Yeah, risk-free is not possible.
No, so that then gets down to knowing where your risks are and making sure that you have mitigations in place to cover those risks should they eventuate. As I said right at the start of this, to me that's prudent design, particularly so in hydromet, and in the contemporary world, I just don't think we see enough of it.
Yeah, but the rule of thumb is you need incentive to put a new technology. Otherwise, mining companies are just why should they do it? You guys had incentives, so in a sense, it was a classic situation where you needed, especially at Langer, you needed an answer really to help. So you were ready to put something new in.
Yeah, even so, that acknowledgement I gave the board at the end of the paper was heartfelt. They embraced a significant risk. Because particularly at Langer, which was then the masthead of the company, this plant dropped right in the guts of it, right in the middle of the process. And yes, we could turn it off, but it wasn't an easy step.
Yeah.
I think the operation of membrane plants, that there's a lot more resilience involved if you get people involved who know how to operate an RO plant. You can really push the envelope of normal operation way beyond that the membrane manufacturers will ever say. But it's engaging that outside expertise. We don't know a great deal about mining, but we know a lot about RO membranes and chemistry. We have laboratory facilities where you can run all sorts of different projections and tests. So I would say try and engage some of the membrane experts.
Okay.
There's also quite significant risk, that gets introduced when you're operating in the extreme pHs and you go over to cleaning cycles. So operating at a very low pH, introducing really dirty process water as a flush, for instance, can result in some serious scaling on the membrane where you have to now resolve a problem that you created yourself. So process water conditions that also change on site, which isn't always perfectly monitored the way that it should be, also tend to contribute to the cleaning side being a quite essential process for the system itself.
Yeah, well, a place like Western Australia, you might have hypersaline water, so your processed water. Yeah. So, but I want to ask a question for the listeners as well, especially. So we know about SX. We need to get down. We need to filter right down to. I like to see it less than 10 parts per million. Some people say 20, and then there's a role for ion exchange, especially resonant pulp and so on. You can start to handle slurries. How does membranes fit into that in terms of what you have to get down the solids down to in order to make it work? The parts per million solids, yes.
It's as clean as possible. Point in case, Langer Heinrich had ultrafiltration, and we were still blocking membranes, the lead membranes with microfines, and we actually installed a cleaning rig. We'd actually take the membranes out and reverse flush to clean out the solids that had built up. Because of the cost of the membranes versus the cost of the labour to do so, it was more economic to turn membranes around to take out the fine particulate solids. So to answer your question briefly, is you want to get that fluid as clean as humanly possible. It took approximately 9 months to get to the point where we started to see the DP issues on stage 1.
When you say clean as possible, what parts per million? What?
Oh, well, ultrafiltration is down at 0.02 micron. And as I say, it took 9 months to block a membrane or to severely restrict the DP on the lead membranes. So you're just putting off an issue. So if you could get it down to 0.001, you would have the
what
membranes.
point does it become a problem? What
DP, you just can't get the flow rate through the plant. If you get large scale on the front end of the plant, you get a high DP. Once you start to exceed your DP, your membrane compression, all those sorts of issues come into play.
There's a measure called silt density index, which is key, where you're measuring the amount of colloids, suspended solids. But the biggest issue is always clay. It's aluminosilicates. That's what fouls the lead element of a pressure vessel. And even with ultrafiltration, clay particles can be down to 0.2 of a micron. So you're even on the borderline with ultrafiltration. The thing with clay is to have some settlement pre-treatment, even sand filters and flocculation, so that you trap all those clay particles so it's as clean as possible going into the RO plant. But also you can remove clay with a better cleaning in place system, using bespoke cleaning products, using things like microbubbles to agitate the clay that's on the membrane surface to help remove it. There's all sorts of new cleaning techniques being evolved to help control that and keep membranes clean. There's some gold mines in the US, in Nevada, where again we've just cleaned 200 membrane elements, cleaned them, packaged them, and sent them back to the mine. And but cleaning in place is really the answer. But it needs some training, some technology, some knowledge on how to do that cleaning process, how to make up the cleaning solution, and then how to recirculate and soak and get the best result in situ.
And that's going back to one of your first questions, Alan, was what are some of the lessons learned? And CIP, design of CIP circuits, that would be, I suppose, one of the key lessons learned coming out of Langer Heinrich.
Is that, Darryl, do you see that as a significant issue going forward? Because having fines and clays in SX and IX, no, that's a big problem.
Yeah, look, Mark's comment is accurate in terms of getting it as clean as you can. You know, we went clarification and UF, and then we started to see some problems within 9 months of operation. The plant had paid for itself 3 times over by then.
Yeah, membranes are minor cost.
Yeah, we could have thrown the membranes out and started again and still been a mile ahead.
Yeah.
So that doesn't, in operation, you still want to reduce those operating costs. That's understood. But is it really material in terms of the decision? Not in the slightest.
What do you do with the membranes after you've taken them out?
Well, we actually had CIP available, so we didn't need to throw membranes away. Some were thrown away. I don't know that was necessarily required, but yeah, no need to. We had clean in place. We were able to do it while those cycles were maintained, while the membranes were looked after. They performed very well.
And Kayla is the exact opposite. Because of the short membrane life, we never cleaned them. So there was no requirement for CIP on the NF membranes. They didn't last long enough.
Well, in a sense, they were clean to death, Mark.
And I suppose, look, that's one of your last questions there, Alan, on membrane life and effect on economics. As Darryl said earlier, it was Kayla Kira's designed for 11 days. I think when you looked into the actual membrane cost on the plant, I think it was 7 hours and it broke even. It was Darryl, correct me if I'm wrong, it was 7 hours life, and we could replace those membranes. Wouldn't be practical, but that was the level of acid savings that could have paid for those membrane replacements. So economics on membranes themselves are actually quite a minor component of the economics of a membrane plant.
Yeah, and even
with a heap of membranes in the dump.
Well, the problem too at 7 hours would have been the membrane industry might not have been able to keep up supply. Yeah, look, these membranes, our experience of membrane plants is that they were really relatively low capital and with significant benefit. Both of the installations, when it came to an assessment, were laid down misères.
Yeah.
And it could be different on different processes. If you haven't got that same level of economics, membranes are arguably your biggest OPEX cost. There's certainly, so if you're not getting the same level of benefits, obviously membrane life is going to become a much more important factor. RO membranes is a classic example. If you're not getting 5+ years out of an RO plant, you're starting to get into, you never get 7 hours to break even on an RO on a water plant desalination. You're talking different ball games.
Yeah.
Yeah, and I think that's one of the challenges as you go back towards like treating PLSs. You've got a lower grade tenor that you're dealing with, so the cost of running the membrane system is greater relative to the, the value that's in it. But yes, so like one of the other possibilities and well, not possibilities, but areas like we look at and work on is the effluent treatment side of things. And both nano and RO have roles to play there increasingly. You mentioned environmental issues, and more people are going towards zero liquid discharge sites. And in that situation, you do have to find a way to manage the effluents. And there's plenty of projects where it comes into play there as well.
Yeah, it seems to be an opportunity to, when you have bleed streams that are potentially difficult to get rid of, maybe it's a new tool to clean up some of these streams that in a relatively inexpensive way, perhaps.
Yeah, I mean, there's plenty of examples of that, and you're weighing them up against and where the brine concentrators and evaporative processes come into play, and even if they are required ahead of that, it can make an improvement to the economics.
Well,
there's been a move towards like reducing tailing ponds volumes, again by using membranes, because you're producing that clean stream of pure water that can be used for environmental discharge, and then concentrating the other. I mean, one of the early big membrane applications was Cananea copper mine in Mexico, where they had a pit that was full up with water and was starting to overflow and affecting the whole of the mine. So they had to dewater it. In dewatering it, what they realised is that the concentrate from the RO plant had enough viable copper there to go back into the extraction process. So they actually dewatered a pit, effectively a tailings pit, and found that there was more copper in that concentrate than there was in that on the process side. And that was Cananea back in the 90s. That was the first really big membrane plant that was applied.
Yeah.
Yes, there's several applications like that. Phosphate manufacturer in Florida, they put in a membrane plant to treat their waste. Hurricane came through and flooded, and it was going into the Gulf. Don't you have to recall, probably 15 years ago, they're actually using oil tankers to take their tailings, put it into oil tankers, and take it out into the Mexico Gulf. And dilution was the solution in that particular case. Over time, we installed a very large, actually it was America's largest membrane-only plant at the time, and we ended up producing from what was a waste stream, boiler feed quality water, 1,000 gallons per minute boiler feed quality water. And they, exactly as you said earlier there, Steve, they found the concentrate could go back into the process. So what started off as an environmental issue ended up as a cost-effective recycling outcome.
Yeah. Well, there's a few, I mean, acid mine drainage is a big issue in the metals industry, no question about that. And there's lots of old pits and things that are still filled with water with copper in it or whatever else is in it. And the authorities are often looking at ways, can you make money out of it to pay for the rehabilitation.
And I think that leads into one of the future developments in membrane materials. Ion exchange resins, we have ion-specific ion exchange materials. currently membranes are valent, multi or monovalent. When we get down a membrane material that is ion specific, that's to me is going to be the next biggest breakthrough in membranes. We can tailor around the edges at the moment in improving membrane performance and different membrane surfaces. But once we can start to get selective with what a membrane actually rejects or transmits, that's going to be the next biggest development.
I was going to ask the question about developments in membranes as to whether there's developments going on that can actually expand their use and make them more specific and so on. So you're saying there is? Yeah.
No,
yeah.
I was saying that's going to be the next biggest step.
Yeah.
There is membranes, there is ways that can be done. At the moment, the membrane manufacturers themselves that we deal with, they're very large organisations that take slow steps.
Yeah.
I think there is certainly work being done. I'm aware of work being done around graphene. It's early days work, but
Yes.
you'd have to imagine it's got a chance of success. And the more I think the mining industry is really good at adapting new techniques, at adaptation of existing techniques, one should say. And I think as membranes become used more and more, as I believe they will be, there will just be more and more potential applications found. As I said earlier, in places where we're not imagining now.
Yeah, but with any, it's the same with SXP solvent manufacturers or IX. There needs to be a big enough market to justify the development work.
Yes.
And, industry will drive the advancement, and it will also push the suppliers into a direction where they realize they need to adapt in order to service that market in particular. Solvent extraction, raffinates, even electrowinning solutions, that has become new drive now, and we see that the membrane suppliers are really stepping up the game to get that additional stability, improve on the flux rates, change the rejections. Even in small applications, they can tailor the membrane specific to the process or the stream that we're treating at that stage. So it will always lead by industry's example, and then hopefully the rest of the guys catch up as we go.
There's about 20,000 membrane plants operating around the world across municipal, industrial. We've found about 350, 390 that are in mining sites now, either enhanced metal recovery or environmental discharge, or a bit of both. That's not an exhausted list. I'm sure there's a lot more, but I think there is a lot more already being used in mining, but everybody keeps it a big secret. This is the first conference I've seen with more than 1 or 2 papers published talking about a membrane use in mining, which is great. But I think there's a lot more already being used. Everybody tries to keep it a bit secretive. As it becomes more widespreadly known, I think it'll be used more and more. But the key thing with membranes is the membranes themselves are now relatively cheap. It's a very proven technology. So it's a much lower CapEx and OpEx risk to just apply it and try it and have a go. I think trying to reinvent to get to selective ions, it isn't really a membrane application, because there's so many plants and there's so many in use at the moment. Really, it's that concentrating stream to then go in another direction. But there's no reason why that concentrating stream using membranes couldn't be applied in a whole host of different water processes, liquors within a mine. I mean, just all the monitoring equipment that you have within a mine and the sampling, they all scale up with calcium sulfate. Using membranes on those circuits can help make sure that all the various sensors and everything else don't get scaled up. So there's lots and lots of different applications. So I think it could be more widespread use.
In the case of construction, the way it got going is the manufacturers, they went around the pilot plants and they demonstrated it and showed the mining companies how it worked. So what is the state of play? How many manufacturers are there? Are they very proactive, or do they rely on people going to the house? How does that sort of area work for the benefit of delegates?
Well, the membrane manufacturers, there's about 6 of large dominant membrane manufacturers, and they produce hundreds and hundreds of thousands of membrane elements continuously to supply these 13,000 membrane plants that are operating around the world. I mean, the biggest plant is Taweelah in Saudi Arabia, which is 900,000 meters cubed a day. 900,000, that's how big it is. I think, we were talking about plants of 75, 100, even 1,000 meters cubed a day on a mining application. This one plant is 900,000. So you can imagine how many membrane elements that is. So the manufacturer's focus is never going to be on niche mining industry from a manufacturer's point of view. But what there are really, really brilliant engineering companies who understand membranes, who have become specialists in mining. So within South Africa, there's quite a lot, like Proxer and Newater and various specific OEMs that are that link between the mining and the membrane industry. So they can build pilot plants, they can get involved in the design once they understand what chemistry and what different extractions are being required. And that's where the drive's going to come. It's going to be in the application of existing membrane technology, which is already developed, proven, and is relatively cheap now. I mean, membrane elements 10 years ago cost $1,000 each. Now they're $500 each. I don't know anything else that's halved in price apart from membrane elements.
Steve, I think that it's a good point. And, seeing the relatively slow rate of change on, say, nanofiltration membranes that can cope with acid environments, but also perform really well, even though we know people are trying to do that. And you look at the tweaks in the people who are the metallurgists and the engineers working with the membranes are off the shelf, almost always.
Yeah, exactly.
The adjustment in the way the process is developed. Darryl's talking about looking at applications for the membranes, and I think you can do tweaks in that. So we might strip or elute sodium chloride instead of sulfuric acid if we think that we develop applications where we've done that deliberately because we know that it's easier for the membranes to recycle the sodium chloride. And so there'll be more thinking of people about how we can use an off-the-shelf membrane and adjust the chemistry once the confidence in the membranes increases as you see more of these commercial applications come online. And, as was said earlier, wanting to be first to be second, we're now really interested because it's been done. And so,
yeah. Well, I think everybody is second now because there's already that many out there.
But I think too,
you just don't know it.
I think the applications we're talking about here, concentration isn't the game. Concentration is only part of the game. The reason we were able to lower operating costs as we did in the discrimination with a monovalent ion, and that's the sort of thing we're talking about. That's the new process tool. We've been able to concentrate for ages. Membranes are a good way of concentrating. I'm not diminishing that at all, Steve. But to be able to discriminate monovalent ions from other ionic species, is a real game changer.
That's a metallurgical tool. Yeah.
That's the tool. Yeah. That's exactly right. So we were able to selectively take out uranium and bicarbonate from within a carbonate bicarbonate solution. Now, when you start thinking about just what you can do with that, particularly when the alkali side of processing is quite large, but it's pretty well aluminium focused in terms of its scale. But you start talking about those sorts of abilities, and the fact that you leave most other metal species undissolved, not in solution. That's where I see the real promise coming.
Yeah.
The use of RO is absolutely. I remember when RO came out in the 80s or maybe late 70s, but I think early 80s, and it was also a game changer. Our access to clean water was suddenly much, much easier and cheaper. Here we've got a way of discriminating. In that keynote address, as I said, we can now discriminate not only on the basis of valence, but we can discriminate on the basis of ionic charge.
Yeah.
That's phenomenal. Now, the ionic charge we've been able to do for a while.
It's a real role for developers like Anstor to do work.
Oh, yeah.
Work on that, so.
Yeah, and you look at the number of metal ion species that are polyvalent themselves. So copper, you could certainly discriminate between copper and iron in solution just by driving all the copper to the cuprous form.
Mm.
You know, that's not hard, for goodness sake.
Yeah. So it's a potentially a new world of metallurgy. Is this what we're saying?
But as alluded to, though, with the number of plants, was it 15 or 20,000 RO plants out there, and you've got 290 industry plants? Just do the math on the numbers. The manufacturers, unfortunately, are still concentrating on the RO membranes, and their R&D is with the numbers, not in the development of new technologies. And it's up to the smaller boutique companies to get these processes up and running, and only then do the manufacturers start to take note.
And research organizations to look into it. Although there's a decreasing number of those, unfortunately, it's another topic. Look, we're now 5 minutes over. I think it's been a great conversation. We probably could go on, I think, on this topic of separation of ions and valencies. That's a whole thing on itself, which sounds very interesting. So I think maybe we should end on that interesting thought and give you appreciation. Thanks very much for joining in, and I know that those attendees have gotten a lot out of it. So Alison, if you're still there, we're going to hand it over to you.
Of course, I'm still here. Thank you, everyone. Thanks for participating. We will go ahead and finalize this video and have it uploaded hopefully tomorrow for on-demand viewers to